All right, so this part of Unit 3 is going to focus around centripetal acceleration and force. Okay, this is important because when we start talking about rotation, you're going to see some of these topics again. But we're going to talk about this here now in just a brief little circular motion talk. So one thing to remember that when we change the velocity of an object, right, one of two things has to change, right? The magnitude, right, or the size, right, or its direction. So when you change that velocity, right, when you change its magnitude, you change its direction, you're accelerating the object, okay? Now, when we look at the linear, right, when we talk about the magnitude, that's pretty much going to be our linear discussion. But when we keep the size constant, we change the direction, now we're looking at our circular aspect, right? So we're looking at our circular motion, okay? Now, if the speed remains the same in the circular motion, we call that uniform circular motion, or simply abbreviated UCM. Okay, remember, physicists tend to be lazy in some regards. Okay, and so we abbreviate uniform circular motion just simply to be UCM. Now, if the speed remains constant, but the direction changes, then the acceleration is perpendicular to the velocity and points in the direction the velocity is turning. Okay, therefore, in uniform circular motion, the acceleration always points toward the center of the circle. Okay, and what we call this acceleration, this is what is called our centripetal, okay, acceleration. Now, remember when we talked about one-dimensional motion, we talked about we don't say the D word. Here we don't say the F word. So we replace pedal with fugal, F-U-G-A-L. Okay, that is not what we're looking for. Okay, now centripetal literally means center seeking. Okay, the prefix centri means center, and in this case, the suffix of pedal means seeking. So what does that mean in terms of a picture? So everywhere along the way, as this object is rotating, it's going to have, right, these velocity vectors that are tangent to the circle. Now, how does the acceleration act? The acceleration is always in towards the circle, okay, in towards the center. And note that these are all perpendicular, right? I can even do here, right, and here, okay? But the acceleration is always going to be into the circle, okay? And so you get this constant motion going around. Here, why not? Let's do this. We don't want to leave this area alone. We didn't put one there, okay? You know, it's not quite, right? So acceleration, velocity, okay? And that's just constant rotating motion. In fact, positive is counterclockwise. So these will all turn, this object would be rotating counterclockwise. So it'd be going in the positive direction. And then the negative is clockwise. If you don't understand that or want to know where it comes from, and some students may cringe right now, but it's the unit circle for math, right? Think about the way the angles orient themselves in the unit circle, okay? So the centripetal acceleration that is experienced by an object is going to depend on two things, okay? It's going to depend on the size of the circle or the radius of the circle, so how big that circle is, and then the speed, right, at which this is taking place. All right, so those are the two factors for centripetal acceleration, okay? Now, the formula for centripetal acceleration is just simply v squared over r, okay? And I do want to also show you another formula. So sometimes the problem may tell you that it takes a certain amount of time for an object to travel in a circle. Well, this is how you find the speed of an object, right? This is one way to find the speed in circular motion, okay? And if we do a complete circle, we're traveling the circumference, and that's what 2 pi r is, right? So the circumference of the circle. Now, how can they kind of try to throw you off a little bit? They may give you the diameter. So you can really do one of two things. You can do pi d, or you can do 2 pi r, right? Cut it in half and then put it back in. Or you can just do pi d. This t is what we call period. And that period is the time to do one cycle of motion. So one complete circle. So if in my previous picture, if it takes 4 seconds to go around that, if I knew the radius, and then I can, and I knew the period, then I can calculate the speed, right? Now, because an object experiences an acceleration during uniform circular motion, that means it experiences a force that we call the centripetal force. Okay, remember, if you have an acceleration, you have a force, and we call that F sub c. Now, one thing is, though, this is not a force like the table we filled in Unit 2, but this, so it's not like friction or weight, okay? It's basically the net force that creates the circular motion. And I want to point out that, yes, we're going to do like an XY chart at some point in time, but I want to tell you that X will treat to be the circular motion, and the Y will be the non-circular components, okay? Because most of the circles will be horizontal in nature, right? So there'll be like a flat circle on the ground. And then, normal force and all that will be acting in the non-circular way. All right, and so here's a couple examples. If excuse me, a typical carnival Ferris wheel has a radius of 9 meters and rotates 4 times per minute, what speed and acceleration do the riders experience? And if a rider has a mass of 75 kilograms, how much force do they experience? Okay, so here they tell us it goes 4 times per minute. So that means it goes around 4 cycles, right, per minute or per 60 seconds. Now, what we want is seconds per cycle. That would be our period, right? So that would be our t. And so all we're going to do is kind of flip this. It's almost like a conversion factor. So we're doing 4 cycles, right? We're doing that in 60 seconds. So 1 cycle would take 15 seconds, okay? Which then allows us to calculate the speed. We have 2 pi over t. So we do 2 pi. The radius of the Ferris wheel is 9. And we're doing this in 15 seconds. And so we are traveling at a speed of 3.77 meters per second. Okay, and now we're going to find the centripetal acceleration because that's what we're looking for. It's going to be AC is v squared over r. So it's going to be 3.77 squared over 9. Okay, and we're going to get a centripetal acceleration of 1.52 meters per second squared. And we can always just assume positive, that's traveling in the, I'm going to split the word a little bit here. It's traveling in the counterclockwise direction, okay? And then the last thing we need to find is find the force. So we're going to do FC equals MAC, right? Because remember, the force is a net force. And so the 75 kilogram rider is experiencing 1.52 meters per second squared in terms of acceleration. And so we'll do 75 times 1.52, not 4.52, and they will experience a centripetal force of 114 newtons. Okay, so our 2 answers would be 1.52, okay, meters per second squared, and 114 newtons of force. Now, one thing that AP Test is doing right now is they're doing ranking tasks, they're called, and so you're trying to determine like how would these rank based on the information given. So you're going to rank these in order from largest to smallest, the centripetal accelerations of the following particles. Okay, so what you're going to do is really find AC for each, right, for each one, and then figure out kind of what will happen is you'll get like a number or a fraction times b squared over r, and you will rank them according to that. So a's would just be b squared over r. B will be 2b squared over r, which means it's going to be 4 times b squared over r. Again, this is almost like a big factors of change thing, right? So like if I were to do the factors of change method, right? Sorry, I'm going to do this in a different color. This would be like 1 squared over 1. Well, that's just 1, right? This would be 2 squared over 1. That's 4. This would be negative 1 squared over 1. Now, note that into the circle is always positive, okay? And so that would also be 1, right? It doesn't matter that will cause this to rotate in the negative direction, and all these other ones are going to rotate in the positive direction, okay? So even when I plug in a negative v, notice I still get a positive number, okay? And so here you got to be careful because this is actually a 2r for the radius, and so I would have 1 squared over 2, which is 1/2, and then here I'd have 2 squared over 2, which is 4 over 2, which is 2, right? And so now I'm going to rank these in order. So which one has the largest centripetal acceleration? Well, it's going to be B, right? Because what number popped out? 4. And then B is going to be greater than E, right? Because E was 2. And then that's going to be greater than, I have half, and I did the 2 ones. So A and C are going to be equal, which then is going to be greater than D, right? And so I just use the factors of change. And if I want to go back, right, and do the equation, well, look what happens. I get v squared over r. Here I'll have v squared over 2r, right? And so it's 1/2 v squared over r. And notice I'm getting the same fraction there. And so this would be 2v squared over 2r. And so I get 4v squared over 2r, which ends up being 2 times v squared over r. So whichever method I use, I still get the same answer because I still get the same fractions out in front. So I get b is greater than e, which is greater than a equal to c, which is greater than d. Okay, so the last thing we have to do in this unit is simply just doing some problems using these, or using the centripetal force and see how it acts.